In this tutorial, we're going to take a look at a test review, the solutions to a test review on equations of lines and planes. If you happen to be taking my Calculus and Vectors course, this is the course code for that course. This is the test for Unit 8 in the McGraw-Hill, that's what MHR stands for, McGraw-Hill Ryerson textbook for the Calculus and Vectors course in the province of Ontario, Canada. And so we're going to start with some multiple choice in the first part, and then some questions that you show some work for. In the first one, it says a vector equation of the line passing through the points 3, 8, and 7, 12 is. And in case you haven't seen the terminology before, I'm using round brackets to represent points, and the square brackets represent vectors. So we find a direction vector for the line by finding the vector between pairs of points, and we have 2 points here. So the points, so here's my direction vector. Some people call it M as well. So we would take the 7 and subtract the 3 from it, and then 12 minus the 8. And so that would be the vector 4, 4. So you can also use any multiple of 4, 4. For example, if you divide them both by 4, you would get the vector 1, 1. You could do 2, 2, or negative 5, negative 5. Any multiple of that would work. So the correct answer is B here. The way it goes is x, y equals, and this is called the position vector of a specific point on the line, and it's pointing from the origin to 3, 8, so it's vector 3, 8, plus t times a multiple of direction vector. I use the 1, 1. If I'd put 4, 4 here, that would have been fine as well. A is kind of backwards. It's got the point where the direction vector would be and the direction vector where the point should be, so that's not correct. This is actually the parametric equations for that line. So if it asks for parametric, then you would answer D. And these are actually the parametrics for that. So this would actually be the vector equation of the line through the point 4, 4 with a direction vector of 3, 8. And E is incorrect here because 3, 8 is a point, but 7, 12 is not a point. It's supposed to be not a direction vector. It's supposed to be just a point on the line. And question 2, it says, which of the following points is on the line x, y, z equals? And I'm going to erase this up here. Actually, I'm going to pause for a moment to do that. And what I'm going to do is I'm going to write out the parametric equations for this line. So it would be x equals the 5, and then minus 3t. And y would equal the 7 here plus 1t, or just 7 plus t. And z would equal the z coordinate negative 4 plus 5t. And I don't know why I put a comma there. It should be a plus. Just erase that. Change it into a plus. Now we're trying to figure out which point is on the line. So we would start. I mean, you can start anywhere you want. I'm going to start with A here. And so what I would do is say, well, if I look at this point, negative 8 is an x coordinate to this point. So if I put negative 8 in place of x here, what I'm going to do now is I'm going to put negative 8 there. So I would get negative 8 equals the 5 minus 3t. And I'm going to solve for t here. So I'm going to bring the 5 over and subtract it from the negative 8. So that would be negative 13 would equal negative 3t. And then I divide out the negative 3. So after those negative 3's divide out, t would be, well, 13 thirds. The negative divided by negative is positive, so t would be 13 thirds. And the question is now, if I put 13 thirds in place of t here, does it generate me a y coordinate of negative 6? And it doesn't, because if I go, okay, so this is 7 plus 13 thirds. So I want a common denominator. So the 7 over 1, I would multiply top and bottom by 3. So it would be 21 thirds plus 13 thirds. And 21 and 13 adds 34. So 34 thirds. And 34 thirds is not the same as negative 6. So that value of t that gave me an x coordinate of negative 8 does not give me a y coordinate of negative 6. And so I don't even have to bother check the 9 here because it doesn't give me the right y-coordinate. So you do the same thing with all the points. Now I'm going to pause for a second and erase a lot of this just to, E is supposed to be the correct answer, so I'm going to demonstrate that that does work. So negative 1 is the x-coordinate here for E, so I'm going to put negative 1 in place of x, and so I would get negative 1 equals the 5 minus 3t. Take the subtract 5 from both sides, or take the 5 over and subtract it from negative 1, so there'd be a negative 6 over here, equals negative 3t. And when you divide it to negative 3, you get t to be 2, because that divides out to 2. So t is 2. Now, so if I put 2 in here, 3 times 2 is 6. And so 5 minus 6 does give me the negative 1. So let's put the 2 in place of t here. So we would get 7 plus 2, which is 9. Okay, so that's the y-coordinate here. And I'm going to put the 2 in place of t here. So 5 times 2, which is 10. So negative 4 plus 10 does give you positive 6. This z-coordinate right here. So that does demonstrate that E is the point that's on that line. Now you could check the other points too. You'll find that none of them, just like the A here, are points that are on that line. So you're trying to find the point that's a specific value of t generates that particular point from the vector equation, or it could be in parametric form too, I suppose. In 3 here, a direction vector for the line x equals 2 plus 5t, y equals negative 3 plus t, and z equals 8 is. And the direction vector are the coefficients of the t, so it would be 5, comma, and then the coefficient of t here is 1, comma. And now z equals 8. Z equals 8 is the same as 8 plus 0t. So the z component would be 0. And that's answer A here. It might be tempting for some people to think of 511. It's very similar because there's no number for t, but if there's no number for t here, then the coefficient is 0, not 1, so it wouldn't be 511. 510, again, 0 because there's no t, so the coefficient would have to be a 0. Question number 4, which of the following points are on this plane? And so what we're going to do is see which of these points actually satisfies the equation of the plane. So I'm going to bring my graphing calculator over here. And you should be able to see all that. So 2, so I'm going to start substituting points in. So my x-coordinate here is 2, going to put 2 in place of x, so it'll be 2 times 2, minus 5. Negative 5 is the y-coordinate there, plus 3 times my z-coordinate is 3. Notice for that point, actually, we've got the coefficients here are actually the same as coordinates of the point. And then minus 4. Now, if that equals 0, the point's on the plane. But it doesn't, it's 34. So then we would go to another point. And so 1, 2, 4 I'm going to check now. So I'm just going to go back and edit 1 there. And I'm going to change that to 2. And then 4 is my z-coordinate. And that is. So 1, 2, 4 does satisfy the equation of the plane. So that would guarantee me that that point is on. And just to, let's do one more here. For example, if I were checking if D is on, I want to put a negative 2 here. Negative, I need to insert my 2. And then 5, so put a 5 in place of Y. And then negative 4, well, I just need to change the sign there. There we go. Works out negative 45. It's not the 0 here, so that point's not on. And you'll find the same thing with this one. Actually, that one's fairly easy to check because if we put 0 in place of x, that's gone. 1 in here, so that would actually be negative 5. And then negative 3 in place of z here that'd be a minus 9. And then minus 4, and that certainly doesn't equal 0. Negative 5, negative 9, negative 4 is negative 18, so again, doesn't work out to be the 0, so that point would not be on that plane. Question number 5. 2 planes that are parallel and distinct, you're asked to find which of these would describe that best. If they're parallel and distinct, let's say that's one plane. then here's another. Parallel and distinct means they're parallel planes. So if I were to draw normal vectors for them, for example, let's say that's normal vector for that one, and this is a normal vector for this one, perpendicular to the plane, so this would be perpendicular. Same idea here. So that's what two parallel and distinct planes look like, and they have parallel normal vectors. The only way they can be parallel is if they're normal vectors. Normal means perpendicular, so this normal and this normal would have to be parallel vectors. Distinct means that they're different, so they can't be coplanar or the same plane. Coincident, that would be the same plane. Intersect in one point. If they're parallel and distinct, they never touch. Intersect in more than 2 points, so again, they don't touch, so they don't have any points of intersection whatsoever. And E is not correct, so are not always the same distance apart. The distance between this plane and this plane, no matter where you are, would be the same. Examples of parallel and distinct planes in most normal rooms would be the floor and the ceiling. If you think of the floor and the ceiling, I mean, unless it's a strange room, an odd room, those are parallel and distinct planes. They don't have any points in common. So that's why C is the correct answer for question number 5. Question number 6, which of the following are vector equations of the plane through the point 6, 0, -2 and containing these vectors? And the way these go, the first vector here is called the position vector of a specific point on the plane. That's the only point we're given. So that's B is the correct answer here. That's why there's a 6, 0, -2 at the beginning here, plus one of the parameters, S, doesn't matter whether you do S or T first or use a different, like a K or something like that for parameter. One parameter times one of the vectors in the plane, plus T times the other vector. So B is the correct answer. You can change, you can multiply one of the vectors by a scalar, like multiply by -1, change all the signs. That's okay. It's just a different multiplier vector in the plane. That's okay. But you cannot do it for the point that's supposed to be on the plane. The point 6, 0, -2 is not the same as the point -6, 0, 2. They're vector opposites. This is not correct because notice it's the vector at the beginning that's parallel to the plane, not the point. I've got the point here, so that's supposed to be a point. It should be at the beginning. And again, kind of similar things done with C here. That's supposed to be, that's a vector where the point should be, and again, that would be here, and that would be over here. Oh, actually, I guess the 6, 0, -2 is the point should be here, and that's the vector, so it should be by one of these S or T's. Last multiple choice, question number 7 here. The lines, these two lines are, and you're asked if they're parallel, coincident, skew, or intersecting. And so notice that they have direction vectors that are multiples. So that means that they're parallel. Now parallel means they could be coincident lines, the same line, or they could just be plain parallel. So it's kind of like, what do we have here? Okay, there's two lines, okay, and their direction vectors are multiples, so maybe this is the kind of situation we have. That direction vector and that direction vector are multiples. In fact, you can see that this one 604 is exactly double the 302. So what I would do to figure out are they the same line or just parallel lines is check to see, is this point on that line or is this point on that line? Okay, one or the other. It really doesn't matter what you do. So I'm going to write out the parametric equation for the second one here, and it would look like this. It'd be 4 plus 6t, and then y equals -1 plus 0t, so just -1, and z would equal 3 plus 4t. So what I'm going to do is check and see if that point 2, 3, -1 is on the second line. So I'm going to put 2 in place of x here. I should have put a little arrow there. I'm going to substitute that. 3 here, and a -1 here in place of z. And you see, well, let me show you the beginning here. This is what most people do. So I put 2 in place of x, so this would be 2 equals 4 plus 6t. So bring the 4 and subtract from 2, so you get -2 equals 6t. Divide out the 6. This actually isn't necessary, but some people would like to see this probably. So t would be negative a third. So the question is now, okay, I've got my negative a third. If I put negative a third in place of the parameter, does it generate the 3 and the negative 1? And I'm not going to bother even do it in the z one here, because you see there is no parameter here. The y parametric equation is y equals negative 1. So that means on this line, every single point has a y coordinate negative 1. There is no t here. So if I put 3 in here, I actually get a non-true statement. 3 doesn't equal negative 1. So that point, because the y coordinate isn't negative 1, could not be on this plane. So that's why they're just parallel lines. I said plane here, I meant line. Of course, if we wanted to put the negative a third here, we'll see that it doesn't give us a negative 1. Although you really only have to get it to not work for 1. You see, it would be 3 and then minus 4 thirds. 3 minus 4 thirds is not negative 1. So that doesn't generate the z coordinate of negative 1. So that's why A would be the correct answer. They're simply parallel lines, not coincident lines. If this point had been on this line, then they would be coincident lines. Part 2, and in part 2 there are several questions where you're asked to show some work. And so in the first one it says find parametric and vector equations for the line through these 2 points. And it says also, once you find those, find 2 points on that line other than the 2 that you're given. So some different points, a couple of different points. So a direction vector, we could find the vector between these, and it really doesn't matter whether you take these coordinates, subtract these, or this in this way. I've done this one minus this one, but you could do it the other way too. So 5 minus 6 is going to be the x. 3 minus negative 2 is the same as 3 plus 2, and 1 minus 0 will be the z coordinate, or sorry, component of that vector. So 5 minus 6 is negative 1, 3 plus 2 is 5, and 1 minus 0 is 1. So that's a direction vector for this line. Again, if you subtract in the opposite order, you would use 1, negative 5, negative 1, and that's okay. There's nothing wrong with that. So possible parametric equations, remember the constants at the beginning are the coordinates of the points. So 6, negative 2, 0. So 6, negative 2, and I didn't bother write the 0 here. You don't have to write the 0, but if you want to write 0 plus t, that's good. And the negative 1, 5, 1 are the coefficients of the parameter t or s. So negative 1 here, so minus t, 5 here, so plus 5t, and 1t here. And you can also do 5, 3, 1, so 5, 3, 1, and then negative 1, 5, and 1 again. You're writing on a different line here, so that's why I use a different parameter. You shouldn't really say this could be or this could be. It's good to use a different parameter here. Now, vector equations. I wrote the 2 vector equations for each of those. Again, this is a point on the line, so the 6, negative 2, 0 goes at the beginning. Remember, that's the position vector of a specific point in that line. It's the vector actually goes from the 0, 0, 0 origin point out to that point, so that's why it's also the vector 6, negative 2, 0, plus t times my direction vector. And again, if we do this one, I'm using the 5, 3, 1. It's just another way to write it, plus s times my same direction vector. Now, so other points. I found 4. You're only asked to find 2. You can substitute any number you want. I used the first one here, the 6 minus t, negative 2 plus 5t, and t ones. So here's my parametric equation. I'm using t equals 1 here. So 6 minus 1 is 5. Oh, look at that. I didn't notice that. So when I put 1 in here, this is 5 times 1, which is 5, plus negative 2 is 3, and 1 in here in place of t. And it gives us the point 531. I didn't notice that it's actually the other point. So, but I found other ones too. So if I was doing that in a test and I had realized that it's actually the other point, I would have gone to another one. Although I've done other ones too here. So if I put negative 1 in place of t here in my parametric equation, be 6 minus negative 1, which is the same as 6 plus 1, so that's 7. Put negative 1 here. So negative 5 and negative 2 is negative 7, and t is negative 1, so negative 1 would be the z coordinate. So 7, negative 1 is a point on that line. Again, if I was doing this test, I would discard the 5, 3, 1. I mean, that's a good example to have done, because it's not actually a different point. 2 here, so we could put 2 as well. If I put 2 in here, 6 minus 2 is 4. If I put 2 here, that's 10, plus my negative 2 would be 8. and then t equals 2, so that's 4, 8, 2 is a point. Again, different from these. And I did negative 2 as well, so put negative 2 here. 6 take away negative 2 is the same as 6 plus 2, so that's 8. Put negative 2 here in place of t, so negative 10 and negative 2 is negative 12, and t is negative 2, so that's 8, negative 12, negative 2. That's another point. So that's how you find additional points on your line. Question number 2 says determine vector and Cartesian or scalar. Cartesian, scalar are the same thing. The reason the letter in Cartesian is often capitalized is because this is actually named after the mathematician René Descartes. Okay, so that's why the C is capitalized, you'll see often. So determine vector and Cartesian equations of the plane containing these 3 points. So you need, for a plane, 2 vectors in the plane or parallel to the plane to get the vector or parametric equations. So I'm going to find the vectors between A and B and then also A and C, and if you want to, instead of one of those, do BC, that's fine, or CB, it wouldn't matter. So I did AB here, so 0 minus 2 is negative 2, and then 3 minus negative 1, same as 3 plus 1, so that would be 4, and then 1 minus 0 would be 1. So AB is a vector negative 2, 4, 1. And I did AC as well, so 4 minus 2 would be 2, 2 minus negative 1 is the same as 2 plus 1, so that's 3, and 1 minus 0 would be 1 again for the Z component. So here's my vector equation, and I use the point A plus t times the negative 2, 4, 1 AB vector plus s times the 2, 3, 1 AC vector. Now, instead of this, and this little notice here, you could have used 0, 3, 1 from B or 4, 2, 1 from C. That would have been fine as well. Now, to get the scalar equations or Cartesian equations, you need a vector perpendicular to the plane. So we'll find that by taking the cross product of AB and AC, or AB and if you did BC, for example. The only difference you might find if you did BC, for example, instead of AC, is you'll get a shorter or longer multiple of this. It still has to be parallel to this normal vector I'm going to find. So this is how and there's different ways to find cross product. This is how I do it. So I write down in this, it goes y component, z component, so 4 and 1, and then back to the beginning, an x component, and then y, so negative 2, 4. And same with the AC, so it goes 3, 1, 2, 3, 3, 1, 2, 3. And so we multiply the 4 by the 1, that's the 4 by 1 product here, and subtract from that 3 times 1. So that's 4 minus 3 is 1 is the x component of the vector. And then, so after we do this, then you go 1 times 2 minus 1 times negative 2. So 1 times 2 minus 1 times negative 2. So that's 2, and this would be plus 2 would be 4. And then for the z component, a negative 2 times 3, so that's negative 2 times 3 there, minus the product of 2 and 4, so minus 2 times 4. So negative 6 minus 8 is negative 14. So those are the x, y, and z coefficients in the plane, this plane scalar or Cartesian equation. So 1x plus 4y minus 14z plus some constant equals 0. And we find the constant by substituting one of the points in. So it doesn't matter whether you use A, B, or C. I used A. I believe I did. Yeah. So maybe I'll move that down enough you can see. So 2, negative 1, 0. So I'm going to put 2 here, okay, in place of the x, and then negative 1 in place of y, and 0 in place of z. And so we solve this, so 2, and then this would be negative 4. That would be 0 here. Now minus 0 plus 0 doesn't matter. So 2 minus 4 is negative 2, and then when we solve for d, we bring that 2 over, it would be a positive 2. So this is the equation with a 2 here. Okay, so that's my scalar or Cartesian equation for my plane. Question number 3 says find parametric equations of a line through the point M, 4, negative 3, 5. Here's my point, and perpendicular to this plane. Now, the equation for this plane, and it looks a little bit fuzzy here, but I have the equation here too. The normal vector or perpendicular vector to the plane would be 2, 1, negative 7. So there's my 2, 1, negative 7 vector. It's supposed to be perpendicular to the plane. So if it's perpendicular to the plane, it would actually be in the same direction as this line. because the line is supposed to be perpendicular to the plane. So the normal from my plane will actually be in the same direction as my line. So that's why I can use 2, 1, negative 7 as a direction vector for the line. So the line has to go through this point with that vector as a direction vector. So 4, negative 3, 5, and we're asked to find parametric equations. So here's my parametric equations. So 4, negative 3, 5 at the beginning, plus, and these are the coefficients of t. So 2t, 1t, and then minus 7t. So there's my parametric equations for the line perpendicular to the plane through the 4, negative 3, 5 point. Now, you could use any multiple of this if you wanted to. So if you wanted to double it, for example, and make it 4 to negative 14, that's fine. If you want to make it the opposite and minus 2t, minus t, and plus 7t, that works too. It really doesn't matter. Question number 4 asks, you're given a couple pairs of planes here and asked, are they parallel and distinct, coincident, which means parallel and the same plane? Are they perpendicular or none of these? So you get 4 things to check on here and explain your answer in each case. So if you look at the 2 planes, and I labeled them, I call this plane 1 and this one plane 2 here. The normal vector for the first one would be 2, 3, negative 8. So 2, 3, negative 8, and 6, 9, negative 24 for the second one. Now these normal vectors are parallel, because if you take this and multiply by 3, you get this one. So this second normal is 3 times the first one. Okay, 3 times 2 is 6, 3 times 3 is the 9, and 3 times negative 8 is negative 24. So we know they're parallel. So the question is now, are they parallel and distinct, or actually are they coincident? Are they the same plane? So the way you tell the difference is you look at the whole equation and look at the constants. You see, if I rewrote this one, I brought the 10 over to write it in standard or scalar form, just like this one is. So the normal vector here is triple the one here, but these constants, negative 10 and 4, are not in the same multiples as the normal vectors are. If I multiply that by negative 3, well, sorry, by 3, sorry, because the normal vectors are in that ratio. If I multiply it by 3 and this ended up being the same plane, then that would have to be a 12 there. So the negative 10 and 4 are not in the same multiple as the normal vectors, so that means that the planes are parallel and distinct. So I wrote here, normal vectors negative 10 isn't equal to 3 times 4, 4 times 3, so that's why they are not the same plane. They're parallel and distinct planes. For B, these are the 2 planes, and they're already in perfect scalar form. Okay, so if we look at the normals to this one, 3, 5, negative 8, and 2, 1, 4. Well, they certainly aren't multiples. Okay, if I multiply 2 by, what number do I get? Well, 1.5 actually. 2 times 1.5 is 3, but if I multiply that y component by 1.5, I don't get 5. And 4 times negative 2 would be negative 8. So they aren't in the same multiples, so that means they can't be parallel and distinct or coincident. Okay, so it says check to see if, so now the other option was, are they perpendicular or perhaps none of these? Okay, so to see if they're perpendicular, see if we had perpendicular planes, this is what they would look like. There'd be like one here, and you know, if this one was perpendicular, let's say that was going up and down. If we look at the normal vectors to the plane, so there's a normal vector to that one, normal vector to this one, okay, perpendicular. So this would be a right angle, and so with this. Then if the planes are actually perpendicular, then the normal vectors would also be perpendicular if they're perpendicular planes. An example of perpendicular planes are in most normal rooms, 2 walls that are adjacent, that meet at a corner. Okay, that's an example of perpendicular planes. And if you think of a vector coming straight over from each wall, then those 2 vectors would have to be perpendicular. So we checked to see if vectors are perpendicular by using the dot product. That's the simplest way to check. So if we take the dot product of these 2 vectors, it should equal 0 if the vectors are perpendicular. So I'm taking the dot product of 2 of these, so I would go 3 times 2 plus 5 times 1, and then minus 8 times 4, or plus negative 8 times 4. So that's 6, that's 5, that's minus 32, works out to negative 21. Okay, so it isn't 0, so they're not perpendicular. So we would call these none of these. They're not parallel and distinct, they're not the same plane, and they're not perpendicular. Question number 5. Find the intersection of this line and this plane. Now, if the line isn't given in parametric form, it's what I'm going to do here is write it in parametric form. And then what we do is we substitute those parametric equations into the plane. So I'm going to write this line in parametric form. So x would equal 3 minus 3t. Y would equal 8 plus 5t. And z would equal 4. And it's just 4 actually because there's a 0 here. You could say 4 plus 0t, but you don't really need to write a 0t. So I'm going to substitute these into the plane. So I'm going to put 3 minus 3t in place of x. So it'd be 7 times the 3 minus 3t. That's what's right here. And I'm going to put the 8 plus 5t in place of y here. So negative 2 or minus 2 times the 8 plus 5t. And then in place of the z, we would put 4. So 4 goes right there. And then we have the minus 71 equals 0 on the end afterwards. So I'm going to solve for t. So what we're trying to do is we're basically saying that this line has points that look like this. You could write any point in this line as 3 minus 3t, comma, 8 plus 5t, comma, 4. Every single point on that line looks like that, has that form. And so when we so every point on this line is in that form. So when we substitute that in here, we're trying to find the point that would be on this line, but also on the plane. So that's why we substitute the parametric equations in place of x, y, and z in the plane's equation. So I'm going to solve for t here. So I'm going to distribute the 7 in. So 7 times 3 is 21. 7 times negative 3t would be minus 21t. Negative 2 times 8 is negative 16. Negative 2 times 5t would be negative 10. Plus 4 minus 71 equals 0. And then we collect like terms. So negative 21t and negative 10t is negative 31t. That's the only t terms we have here. And then maybe we should a little arithmetic here. So the constants, we get several of them. There's 21. Minus 16 plus 4 minus 71. Make sure my math's right here. So that's minus 62. So I want to solve for t here. Let's get rid of the calculator. So I'll bring the 62 over the other side. It's positive, so divide with negative 31. So 62 divided by negative 31 is negative 2. So negative 2 is the value that will generate a point on this line that's also on the plane. So we find that point by substituting negative 2 into the parametric equations. So x equals 3 minus 3t, so I'm going to put negative 2 here. So that'll end up being a plus 6, so 3 plus 6 is 9, so the x coordinate's 9. And then y equals 8 plus 5t, and we'll put the negative 2 here. That's negative 10, so 8 minus 10 is negative 2, and of course z is 4. So that point, 9, negative 2, 4, should be on this plane. And we can verify that. Let's see, where's my plane's equation? Ah, here it is. So 7 times 9 minus 2 times the negative 2 plus z, so that's the 4, remember? Minus 71. And of course we should get 0 if the point's actually on there. Oops, what did I do wrong? Oh yeah, I used the subtraction sign there, so let's fix that. Instead, a subtraction sign instead of the negative. And it does work out to be 0, so that point is on the plane. Question number 6, describe all the ways two lines can exist in 3 space and the types of intersections they have or don't have. Two lines. So 2 lines might intersect in a point like this. Just like in 2-dimensional space, the drawing would look very similar. They cross and they intersect, they have 1 point in common. Okay, so 2 lines could exist having 1 point in common. They could also be parallel and never intersect. Parallel and distinct lines, distinct meaning they're different, like this, kind of like 2 railroads. If you look at a railway, the 2 rails look in one direction, look in the other, same distance apart everywhere. Okay, so that's an example of 2 parallel lines that never ever intersect. The third way is they're called skew lines. They're non-parallel lines that don't intersect. And in 2 space you can't do that, but in 3 space you can. And so this is what it looks like. If you think of, okay, so these are 2 planes with 2 lines. The red one lies in the top plane and the brown one lies in the bottom plane. And those lines are not parallel, but they don't intersect because there's some shortest distance between them. Here, I'll give you an example. If you have a normal desk, a desk that's parallel to the top is parallel to the floor. So let's say that this is the floor and this is the desk. And let's say you dropped a pencil on the floor and the pencil on the desk. Now, it could be that you dropped them at the parallel. That is possible, although not too likely. They would be, as long as they're non-parallel, they're going to be skew. So this one lies on the floor, this one lies on the desk. And so if you extend them out infinitely in each direction, they would never cross because the shortest distance between them is the distance between those 2 parallel planes. Okay, so skew lines are 2 lines that lie in parallel planes, parallel and distinct planes, but never intersect because there is some shortest distance between them. Question number 7, and there's 2 different questions here. You're given 3 planes and asked to find out where or how they intersect. And if they do, and that's possible they might not. So, and you're asked if the solution is infinite, and that would normally be the equation of a line, or it could be a plane too. If it's infinite, find the equation of that thing, that line or plane. And then find one particular solution. So a particular solution is an example of a point that's on that line or plane of intersection. So make sure you describe the type of solution. So the first one here, here's my 3 planes. And so I'm going to bring the constants over, so that's why it's the 3. That'll be a -7 and a -9. And I'm going to solve this by elimination, just like you probably learned in grade 10. With 2 equations and 2 unknowns. And so I'm going to call this equation 1, this 2, and this one 3. So that's my labeling there. And you choose to eliminate a variable. I did z here, but you wouldn't have to do z. You could do x, you could do y in 2 different pairs. So there's 2 different pairs of eliminating here to eliminate the same variable to get 2 equations that no longer had that variable, just the other 2. So I eliminated z's here. So I took the first equation, that one right there. So notice that's exactly the same as number 1. And the second one, I took this second equation and multiplied everything by 5. So 3x times 5 is 15x, 4y times 5 is 20y, -z times 5 is -5z, and -7 times the 5 is -35. And the z terms are opposite, so we would add. So x and 15x add to 16x, -3y and 20y add to 17y. These z's are opposites, they add to 0. So we've eliminated the z. And 3 and -35 add to -32. So this is an equation that no longer has z, it just has x and y. So because it just has x and y, that's why in the next time you want to eliminate z again, but with a different pair of equations. I used 1 and 2 here, so over here you can do 2 and 3, or you could do 1 and 3, it wouldn't matter. Just a different pair than 1 and 2. So I did 2 and 3. So notice that these have the same z coefficient, -z. So these 2 can just be subtracted to eliminate the z's. I don't have to worry about multiplying by constants. Now some people might like to always add, and like if I wanted to multiply one of these by -1 to make these opposites, that would work too. Okay, but I can subtract here. So 3x minus 4x is -1x, 4y minus 2y is 2y. The z's are opposites, the same, so they subtract to 0. And -7 minus -9, same as -7 plus 9, so that'd be a 2. So this equation I'm calling 5, and this equation I'm calling 4 have x's and y's only, no z's. So I can now eliminate x or y, and then start solving for a variable. And I chose to eliminate x over here with these. So noticing that I can do a little bit less multiplying if I do x. You see, if I did y, the least common multiple of 2 and 17 would be 34. So I'd have to multiply that by 17 and that by 2, and then I would have 34y for both. But because this is just -x, if I just multiply that by, well, either 16 or -16, I'll get the same coefficient here or the opposite. So here's my 4, my same equation is here, and I multiplied this by 16. So that would be -16x, 16 times 2y is 32y, and 16 times 2 is 32. And so opposites add to 0, so we add here. 17y and 32y is 49y, and negative 32 and 32 add to 0. And so I would divide by 49 both sides to get y is 0. And as soon as you know that a coordinate, then you can start solving to find other values. I know y, so I now can find x and then z. And why I'm doing x next here is because these two equations, I can use either one. If I know y, I can find x. They link x and y. So that's why I would choose to do x next. And so I took this equation number 5 and I put 0 here in place of y. So 2 times 0, of course, is 0. So that term just disappears and we get negative x equals 2. So dividing out the negative 1, I get x to be negative 2. And now that I know x and y, I can find z. So I went back to this very first equation here. I need to scroll up a little bit. So that one right there is the one I'm using. And so I'm going to put 0 in place of y here and negative 2 in place of x. And so negative 3 times 0 is 0, so that y term's gone. So it's just negative 2 plus 5z equals 3. And so I'm going to add 2 to both sides, or bring the negative 2 over. So 3 added to 2 would be a 5. And I divide to 5 and get z equals 1. And so the three planes intersect uniquely, which means at a single point, at the point negative 2, 0, 1. So there's a single point of intersection. An example of that, and the planes don't have to be parallel, but if you were in a normal room, if you look at two walls where they intersect in a corner, and let's say the floor, you look down the corner, well, that point where the two walls and the floor meet, that's the unique point of intersection, the only point that's on all three of those planes. In B question here, number 7, so here's our three planes, and I'm going to label them 1, 2, and 3, and bring my constants over, so it'll be a 1 here, and this would be 2, and this would be a 3. So there's my three planes, and again, choose to eliminate a variable. I'm eliminating x in this case. I did z first in the last one. So x and x is fairly simple because you see these two equations both have a 1x. So there's my one equation, and 3 is my second plane. And so I can subtract them. 1x minus 1x is no x's. So negative y minus, there's no y's here. Negative y minus 0 would be negative y. Z minus 2z would be a negative z, and 1 minus 3 is negative 2. And because all the coefficients are negative, you don't have to do this, but because they're all negative, I just divide by negative 1 to change them all to positives. So it'll be y plus z equals 2 instead of negative y minus z equals negative 2. Now notice that this is the same as the planes equation we didn't use to eliminate x. So that means that these planes are multiples of one another. Okay, so this is the same as the other one. So see, if I were to take this and subtract this, like let's say I want to eliminate y, I actually would get, this is what it would look like if you didn't notice this. So here's my y plus z equals 2, and here's the one I just got, y plus z equals 2. Okay, so let's say I said I'm going to eliminate y, I'm going to subtract. So that would be 0, and that would be 0, oh, and that would be 2. I just get the true statement that 0 equals 0. So if you get that kind of thing, a true statement like that, and of course if I wanted to, instead of putting a 0 here, I could call it 0z equals 2, sorry, 0. And that's a true statement no matter what number you put in place of z. 0 times anything is 0. So, the planes are linear combinations of each other, so they intersect in a line. And so what I need to do now is find the equation of that line of intersection, because that's what the instruction said in number 7. Find the so it's the line of intersection, find the equation of that line, and then also demonstrate a point on that line. So I'm going to take this y plus z equals 2 equation, and I'm going to let z equal t. If I wanted to use y equals t, that's okay too, it wouldn't matter. But I chose to make zt, so I'm going to put t in place of z here, and solve for y, so bring the t over, so y would be t minus 2. So that's my parametric equation for y for this line of intersection. And then, so I'm going to go back to one of these to find what x is. So I chose this one. I could have used a different one, it wouldn't matter, but I chose to use the third one here. X plus 2z equals 3. So I'm going to put t in place of z, because remember, z is t here. So bringing the t 2t over, x would be 3 minus 2t. If I chose a different line, plane, it wouldn't matter. So let's say I chose this one instead, just to demonstrate. So x minus y plus z equals 1. So again, this is my y here, so I'm going to put that in place of y. 2 minus t. Remember I said z was t, so t in place of z. So taking the brackets out, we get negative 2 plus t equals 1. So x minus 2 plus 2t equals 1. So I'm going to bring this negative 2 over and add it to the be positive 2 over here. So that will give me 3. And when I bring the 2t over, it would be minus. So there's exactly the same equation I got a moment ago. Right there. So my parametric equations are x equals 3 minus 2t. We found a moment ago here that y is 2 minus t, and I said z equals t. So that's the equation of that line of intersection. So now we need to find a point on that line. So we find a point on that line, what I call a particular solution, by substituting a value in place of t. You use any number you want. I use 1 here, so I put 1 here, here, and here. So 1 here. So 3 minus 2 times 1, 3 minus 2 is 1. I put 1 here, so 2 minus 1 is, of course I do the same number, as 1, and z would be 1. If I instead, let's say, did 0, just to demonstrate another point, so let's say I put 0, then x would be 3 minus 2 times 0. Actually, you can see this one without even doing the math. 2 minus 0, well, not y, z. Erase that. Z equals 0. So this would be 3, this would be 2, this would be 0, so that would be the point 3, 2, 0. Which if you look at the lines equation, 3, oops, I'm looking here, 3, 2, and there's no number here, so this is like 0 plus t here, so 3, 2, 0 is a point on that line. So the point 1, 1, 1 or 3, 2, 0 are points that are on that line of intersection of these three planes. Okay, so it's a common point to all the planes. Question number 8, the last question here, I believe it is. This one asks to determine the exact shortest distance from this point, 3, 1, negative 2, to the plane. And this is kind of similar to an earlier question where you asked to find that line of intersection is perpendicular to the plane. But in this case, you're asked not just to find the equation of this line, but the distance from that point down to the plane. And the shortest distance, not, for example, like that distance. Okay, that wouldn't be the shortest distance. It would be called the perpendicular distance. The shortest distance down to the plane. So the distance from here perpendicular down to the plane. And this Q point comes in later. You wouldn't know this right away. So we'll get to that in a few minutes here. So we need to do what we did in an earlier question to find the equation of this line, this perpendicular to the plane, because the perpendicular distance is the shortest distance. And so this point here is called the foot of the perpendicular, okay, from that point down to the plane. So the plane that we're given here, 2x plus 4y minus 5z plus 25 equals 0. The normal vector for that plane would be 2, 4, negative 5, or a normal vector, or any multiple of it. So that vector would be perpendicular to the plane, like this purple vector here. So it's also in the same direction as this line of intersection is coming, which should be the bottom of this foot of intersection here. So I'm going to use the 2, 4, negative 5 as a direction vector for this perpendicular distance line. And so the line goes through the point 3, 1, negative 2, so parametric equations 3, 1, negative 2 here, and then 2, 4, negative 5 for the coefficients of the t. So this would be the parametric equations of this line perpendicular to the plane. So once I find the line, what I want to do is find out where does that line intersect with the plane. This is how I'm going to get this Q point. to find that intersection point. So, and a few questions ago I did a question where you find where a line intersects a plane. So same idea. We're going to substitute these into the plane's equation. So I'm going to put 3 plus 2t here. So 2 times the 3 plus 2t, that's that. And I'm going to put the 1 plus 4t here, so 4 times 1 plus 4t. And then negative 2 minus 5t here, so minus 5 times negative 2 plus 5t. That's that there. And of course, the plus the 25 equals 0. We're substituting that into the plane's equation. And so we distribute 2 times 3 is 6, 2 times 2t is 4t, 4 times 1 is 4, 4 times 4t is 16t, negative 5 times negative 2 is 10, negative 5 times negative 5t is 25t, and plus 25 equals 0. So 4t and 16t is 20t, plus 25t would be 45t. And the numbers actually, okay, 6 and 4 add to 10, and 10 more is 20, and 25 would be 45. So we get 45t plus 45 equals 0. Bring the 45 over, it's negative 45, and then divide out this 45. So t works out to be negative 1. So if I substitute negative 1 in the equations of the line, then that's how I get this point here, this q1, negative 3, 3. That'll be the foot of the perpendicular down to the plane. So putting negative 1 in here, so 3 plus 2 times negative 1, so this would be 3 minus 2 is 1. Negative 1 here, so 1 plus 4 times negative 1, so basically it's 1 minus 4 is negative 3. And the negative 1 here, negative 2 minus 5 times negative 1. Now this ends up being a plus 5, so negative 2 plus 5 is positive 3. So 1, negative 3, 3, that's the coordinates of that foot of the perpendicular. So that's where I got this Q point from. So again, exact shortest distance, what's the distance from this point to this point? Now what I'm going to do, you could actually use the distance formula, but what I'm going to do is just find the vector from P to Q, or I could do Q to P, and just find out how long it is, because that's my distance. So the length of vector PQ, and actually let's, I need to probably do a little scrolling here, I suppose. Actually, let's do this. Let's just take a little picture, and just so we can see these when I go to do the paste. There we go. Okay, so I'm finding the vector from, I'm calling it PQ, so Q's minus P's coordinates. So 1 take away 3 would be my X component, which is negative 2, and negative 3 minus 1 is negative 4, and 3 minus negative 2, same as 3 plus 2, so that's 5. So the length of this vector PQ would be the root of, and this is really distance formula or Pythagoras' theorem in 3 dimensions, the root of this squared plus this squared plus this squared. So we square the negative 2, the negative 4, and 5 and add them up. So negative 2 squared is 4. Remember, negative 2 times negative 2 is a positive. Negative 4 squared is 16, and 5 squared is 25. So that's 20, and 25 adds to 45. Another 45 like we got up here. And so exact shortest distance, I want to, it's nicest to write this as a radical and simplest form. So 45 can be broken down to 9 times 5, and I'm using 9 because it's a perfect square. The square root of 9 is 3, so then it ends up being 3 root 5. So it's actually a fairly nice small solution, not some humongous fraction or something like that. So the distance from P to Q would be 3 root 5. So 3 root 5 is the shortest distance from this point down to this plane. And that's the end of the review.